In this section of the presentation, we will discuss how to calculate the pressure of a gas due to all the particles in the container. And just a reminder, we just calculated in the previous slides pressure exerted due to one particle on a wall that is placed perpendicular to the x-axis as equal to mv squared lowercase divided by v, where m is the particle mass, lowercase v is the velocity, and large V or the capital V is the total volume of the container. Now we extend these ideas to calculate the pressure due to all the particles. One important thing that we would say is, well, if one particle exerts certain pressure P, n particles should exert a pressure of n times P. But you will quickly realize this may not be the case. Now let's say that each individual particle has a different velocity. Let's say each particle has v1, v2, v3, etc. velocities. If that is the case, a general situation, we can write the pressure exerted by all such particles will be simply equal to m, the mass of the particles, multiplied by the square of their velocities divided by volume, and sum this series. So that series is simply equal to m, which is common to all the individual terms of mv squared over v. And so if you take out of the fraction, v1 squared corresponds to the term emanating from molecule 1 or particle 1, and v2 squared is from the second particle, v3 squared, third particle, etc., till v squared sub n, which corresponds to the last particle, the nth, and divided by the volume V, which is common to all the terms. So you have a common denominator, and you're multiplying with the mass, which is common to all particles, and the summation of squares of velocities. So this is simple enough to calculate the pressure of all the particle pressure exerted by all the particles, except for one problem, that is, we do not know the velocities of individual particles 1, 2, 3, 4, 5, etc. Now remember, these are the velocity components along the x-axis for those particular particles. So we still keep that in mind, the velocity component along the x-axis. So now we can write this sum in a very interesting and simple form in terms of the average velocity. Average velocity is given the symbol parenthesis v squared along the x-axis. So that is equal to v1 squared plus v2 squared plus v3 squared plus v4 squared vn plus vn squared, the last term, and this sum needs to be divided with the number of particles n. So we can now convince ourselves, if we sum this series and divide with the total number of particles, we should be able to get average squared velocity as written here. So now in the above expression for the pressure by all particles, I can replace the numerator with n times v squared average, right? So taking these terms to the other side, I can say the sum is equal to v squared average multiplied by n. So making this substitution, we can make a simple simplification of the above equation is equal to P, the pressure due to all particles, simply equal to the mass of one particle multiplied by n, total number of particles, average square velocity, divided by the volume of the container. So still we're in a bit of a trouble here because we are looking at average velocity squared along the x-axis. And however, this will be rather difficult to measure. So we would like to instead write this as the average velocity in any given direction. And we can readily do so by looking at the vector analysis. For example, we can say that the x component of the velocity v is related to the average squared velocity as equal to square of c squared, and if we drop the direction, so that is the average direction, is equal to u squared plus v squared plus w squared, where u, v, and w are the velocity components along the y-axis, x-axis, and the z-axis. So that is the average squared speed, as we defined in the previous slides, is simply equal to summation of all the three averages along the x-axis, y-axis, and z-axis. Right? This is simple vector analysis. So the direction is averaged out depending on the individual components and their individual directions, x, y, and z. Now I can write this in a very simple way as equal to 3 times average v squared along the x-axis. How I can do that? And that is velocity components, u squared, v squared, and w squared, will all be equal after you have averaged them out. Why? That is, u squared average will be equal to v squared average, and that's equal to w squared average. Now you might ask, why is that? That's because if the gas is not flowing, if the gas in the container is stationary, which is the case, then any one of the 3 components should not exceed the others. That is, if the velocity of the gas along one direction, let's say x-axis, is faster than the y and z-axis, then the gas will escape the container through the wall perpendicular to the x-axis. Clearly the gas is not moving, it is stationary on the whole inside the container. Therefore, when we average the squares of all these velocity components along the 3 axes, they should be exactly the same. If each of these terms is exactly the same as the other term, then the c squared average will be reduced to simply 3 times average v squared, or 3 times average u squared, or 3 times average w squared. It doesn't matter at that point. So having recognized then, we can that average c squared is simply equal to 3 times the average squared velocity along any particular axis. We can replace our v squared in the pressure expression that we have derived. So v squared then equals to 1/3 c squared. Okay, 1/3 c squared. So now, since the gas is not flowing, we can simply write pressure times volume in the above expression is N times V times 1/3 c squared. So we call this as PV equals to 1/3 NMC squared. It's very useful to familiarize yourself with this expression because we used it before. We're going to use it again and again and again. So this is a very useful equation which we have derived so far from fundamental principles applying Newtonian mechanics. So again, pressure of the gas multiplied by the volume of the gas is equal to 1/3 NMC squared. So let's look at it from a different point of view. Pressure times volume, if you look at the units, simply equal to the energy, units of energy. You can convince yourself by explicitly writing the units and reducing them into joules. Okay? It goes 1/3 NMC squared. And so that's the kinetic energy, right? 1/3 is a constant, n is the number of particles, m is the mass multiplied by c squared. So you know 1/2 mc squared is kinetic energy. Therefore, we have found a simple way to relate the pressure volume energy, which is the P times V, to the kinetic energy of the gas. This is what we did several slides before. We derived the kinetic energy of a gas molecule using this expression backwards. This slide, we're going to look at the pressure of the gas in slightly more detail, how it is related to these other quantities we just described, macroscopic quantities relating to microscopic quantities. First, we would say that pressure of the gas is related to directly the number of particles in the container. So if I increase the number of particles in our container, we'll see higher pressure. This is very evident in a day-to-day basis. Like, for example, your bicycle tire. As you pump more air particles into the bicycle tire, the tire having a fixed volume, the pressure increases. So the pressure is proportional to the number of particles. As you increase the number of particles, keep the volume constant, pressure should increase. So increases with number of moles, which is related to the number of particles. The pressure also depends on the mass of the particles. So heavier particles may exert higher pressure according to the above equation, PV equals to 1/3 nmc squared, where small m is the mass of the gas particles. It's also related to the average speed, c squared average. In other words, in fact, we measure the pressure and volume. From that, can calculate the average speed of the gas particles. We know the number of particles present and the mass of each gas particle. So this is a wonderful way to try to understand the macroscopic properties such as pressure and volume in terms of microscopic properties such as the mass and the average squared speed. So this is a very useful insight that we obtained by modeling. Now, we made several assumptions in this and the previous slides. So we need to discuss the justification for these assumptions, and we ask, are these reasonable? Okay, so the first thing we want to say is, if the particles are not moving parallel to the x-axis, can we write the same expression? We know fully well that as the particles are moving randomly, not that all of them moving along the x-axis, they're moving in all different directions. And therefore, we will ask, how do we understand that in respect to this? Well, that's very simple. All we do is assuming that any particle moving in any given direction can have velocity components along the x, y, and z axis, which are the u, v, and w velocity vectors. And therefore, we always can decompose the velocity along any given direction in terms of the velocity along the x-axis. And this is exactly what we have done. We have related the velocity along the x component along with all the components along the other axes and equated that to that of the average. So we have indeed utilized this idea that the particles may not be traveling parallel to the x-axis. Okay, this is a very important consideration that we have to understand. Now, the second issue that we have chosen, a particular vessel of particular shape. Is this important? We have assumed that we have a rectangular box with a square cross-section. Now, you can ask, well, is this really relevant? What would happen if we have a spherical box? Now, the pressure of the gas is isotropic, means it is the same in all directions. So, if I have a vessel that is a square, or if it is a sphere, or any other property, the pressure exerted at any given point should be exactly the same as at any other point. So, the use of a rectangular box is actually a convenient way to describe, and irrespective of the shape, the gas pressure should be the same. So this is an important consideration that we need to keep in mind. Now, we also assume the particles are elastic, making elastic collisions with the wall with each other. This is very important. If this breaks down, of course, then you're going to be lost in the kinetic energy, and the gas at some point will come to rest. This is not happening. We don't see that gases condensing spontaneously into liquids, and therefore this is a pretty good assumption to work with. However, we also assumed that the volume of the particles are negligible, and we also assume the interparticle interactions are negligible. So these two assumptions that we made need to be updated, which we're going to do that when we discuss van der Waals equations. So except those two assumptions, all the rest seem to be quite good so far. So let's move on to the last piece of this part of the lecture. That is one piece that we still need to cover, and that is Graham's law of diffusion. And this is an assignment for you to read in the book and approximately write a 200-word report and use a particular graphic to explain the concept, and then maybe even put out a short problem that can be used to calculate the diffusion coefficient, the molecular weights, or any other aspect of this particular law. And so part of the mission in this course is to test you and see if you can actually, teach yourself. And I'm sure you can, and you will. And we're going to ask you to, sharpen this skill to get better and better at teaching yourself. And this is the most important thing in our daily life, that how we learn by ourselves. We may not have people to teach us everything we need to know. So we need to develop this skill really well so we can actually teach ourselves complicated concepts, etc. So we'll start with something simple, and then as the course moves on, we'll give slightly more and more advanced assignments of teaching yourself. And we want to develop your self-confidence and say that you actually can teach yourself very well even the most complicated topics. That's what we want you to realize and recognize and utilize in this course. And as usual, in the last slide, we basically have some examples and problems. These are self-explanatory, and you can look at the textbook or any other book source and think about at least one example of an application of ideal gas equation in everyday life. It need not to be perfect, it need not to be exact, but I'd like you to think about how you relate what we learn in the class here or in the lectures to the everyday life. And this is an important aspect. Try to get a better understanding that what we're discussing here is not something totally abstract. There are certain abstract concepts that we're putting forth, but these are down-to-earth, everyday life experiences. And so it's important to make that connection. In terms of problems, work out at least 3 problems from any book which use ideal gas. Explain why is it essential to make these assumptions that it has to be perfectly elastic. I sort of alluded to that during my explanations. What will be the consequence if this assumption is not correct? And third problem is calculate the temperature of hydrogen molecules when their average speed is 100 meters per second under 1 atmosphere pressure and when the gas occupied a volume of 22.4 liters. And this is just a problem to demonstrate we can do these sort of things pretty readily.